An example that I want to do in Python is going to be this problem 2, which is this mesh is actually the same mesh as before. But now instead of giving us all the nodal displacements, we're only given the essential boundary conditions, and we actually have to solve the problem. So we want to get the correct displacements for nodes 3 and 4, given the material properties and the body force vector. So this is gravity. So this object is subject to gravity. So we need to compute the stiffness matrix for each element. We need to assemble into the global stiffness. We need to compute the force vector for each element, assemble into the global force vector, set up our system of equations, and solve for the unknown displacements. So let's do that. The mesh is the same. So, I mean, for completeness, I'll go back and get the mesh. Not the node U, because now the node U is not known, but the mesh is the same. So I have the mesh, right? And I need to assemble the, well, get the stiffness matrix for element 1. And so for the stiffness matrix of element 1, if you go to the nodes, what is the stiffness matrix for the triangular element? It's just, well, it's the integral of B matrix times D times B matrix. And then for the constant strain triangle, the integral, I don't have it in the notes here, but the integral is just the area. So just area times B matrix times D times B. And then I put the D in a different set of nodes. So I need to go back and take a look and find that. I'll do that in a second. So I need, first of all, I need the B matrix, right? So I need the B matrix for this element, calc B, and that one needs x1, y1, etc. So I need to get x1, y1, and so on. So I'm just gonna reuse what I have before. And then this for element 1. So this is for element 1. This is what I was saying, that it's very convenient because now this works for any element. And then so the node occurrence, the B matrix, the area, I just need, I forget what is the name of the function that calculates the area. It's just called area, okay. Again, it's a function that is defined above, so area, and then I need the D matrix. The D matrix has material properties, and that one, I wonder if it appears here because I've used it before. It's not there, so I'll have to find it very quickly. It's in the book. Where is? Oh, it's not 274, sorry. Oh, here it is. Yeah. No, I don't know by memory. And there's two options. There's either plane strain or plane stress. So that D matrix, or either plane stress or plane strain. I don't know if I specify something in the problem here. Did I say plane stress problem? Okay, plane stress problem. So that means that out of the two, I need the plane stress one. So again, this one, it's in chapter 9 of the book. You just need to look that up. So E over 1 minus V squared. So let's say that I have E and I have nu, And so this is E over 1 minus new square times MP array. And then I think it's 1 new 0, then new 1 0, and then the last row I don't remember. Okay, so 1 new 0, new 1 0, 0 0, 1 new over 2, 0 0, 1, wait, what was it? 1 minus new over 2. All right, and for my example, new is 0.25, epsilon is Young's modulus is 10 and 0.25. All right, so then the stiffness matrix for this element is just the multiplication MP dot of BE transpose and then MP dot of DBE, and all of that times the area. Okay, E1. And let's see where I messed up. Okay, it's array, not. There we go. So that's the stiffness matrix for element 1. Again, just B transpose times D times B. And then the D is the material properties. I just got that from the book. And then the B matrix, we just created that function. That function is just a function that given the x1, y1, x2, y2, x3, y3, it just assembles the correct this matrix for the constant strain triangle. Again, it only depends on the nodal coordinates. That's it. So do we need to do this? We need to do the same thing for element 2. But before we do that, we'll do the assembly. So for that, because this is the first time that I'm introducing the, actually before I do that, I'll do it here. I'll initialize the global K. So the global K is going to be matrix of zeros, and here this one is important. This one is 2 times the number of nodes, because we are solving 2 problems. We are solving for x and y components. So this one, the K is 2 times the number of nodes times 2 times the number of nodes. Again, because we are solving for both the x displacement and the y displacement. Just good to keep in mind. For the heat transfer problem, this was just n node by n node. For the elasticity problems, it's 2 times the number of nodes times 2 times the number of nodes. Okay, so I have that. And then I'm going to assemble into this. When we do assembly, basically we need to know each one of these KE1 entries. There's a lot of them. But for example, where does the 0, 0 entry of the K1 go to for the global stiffness matrix? And this one is a little bit tricky because this one, the 0, 0, 0, 0 in KE means n1x, n1x, right? But what is n1x? I have n1. n1 is the number of the node, right? So this is, for example, for the first element, this n1 is just 0, then this is just 1, and this one is 3, right? But what do I mean by n1x, n1x? And then, I mean, I can put that here, n1x, 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 And then the second one, if I do 0, 1, that will be n1x, n1y. If I do the next one, it's gonna be, if I do this, this is n1x and 2x, etc. Right? But what is n1x and what is n1y? I already have n1, n2, and 3, but I need to get n1x and n1y. What is that? And what you need to see is that, for example, here you can see that for the local stiffness matrix or the element stiffness matrix, these both correspond to the first node of the element, but x and y, then x and y, then x and y. And if you see that our global stiffness matrix is actually 2 times the number of nodes times 2 times the number of nodes. And this is because for every node we have x and y. So n1x means I need to take n1, right, and then split. So out of n1 I need to get a value for n1x and a value for n1y. And so the way I'm gonna do this is like this. So n1y is gonna be the node times 2 plus 0 and the node times 2 plus 1. So you can see that now from every node number I am going to get 2 different numbers, right? And this, the reason for doing it like this is because this eventually, if I use all the nodes, I will use basically 2 times the number of nodes. So this ordering, what it will guarantee for the global stiffness, basically you have n1, the global n1, n1y, n2x, n2y, n3x, n3y, etc. And that's why you have 2 times the number of nodes. And so you can continue. So n2x is just n2 times 2 plus 0. So you do the same thing for all of them. So n2y. So out of n1, n2, and n3, I am going to get 2 numbers. And then now I can do all of these, etc. I'll just do it. This is very tedious. Actually, I don't want to do it. You would have to do every single one of these 36 lines of code. You would have to do this and then this. So 36 lines of code, not very efficient. You can do it with 36 lines of code, but is there a better way of repeating this? Well, how do I repeat things with a for loop, right? So I will need some sort of for loop. And then I know that what is 36? 36 is just 6 times 6, right? So I need 2 for loops that go from 1 to 6. That's what I need. So for n1 in range, ni in range 6, for nj in range 6. And then what I need to change, you can see that the things that change in the for loops are these guys are gonna go from 0 to 6. So here I know, for example, this is 0, and then this is gonna go 0, 1, 2, 3, 4, 5. Then this is gonna change to 1, and then this is gonna go 0 to 5, and so on. So that one is already captured with ni. And then how do I change the n1x to read the different n1x and ny? I'm just gonna put them. I'm gonna call it node map, for example. I'm just gonna put all of this in some list that I can read off. So n1x, n1y, n2x, n2y, n3x, n3y. And so here I am just going to read out of that node map. It's not x necessarily. Let me just call it I. And here, let me call this ni. So ni, I'm gonna read out of the node map the ni. So you can see that this will read not ni, need to read I. It will read n1x, n1y, n2x, n2y, n3x, n2y, you know. And then the second one will do the same. There we go. So now I is basically the same, like 0, like I and j are gonna be this 0, 0, 0, 1, 0, 2, and then ni and nj are the corresponding n1x or n1y and so on. So now I can do k of ni and j plus equal ke1 of ij. So this saved me the 36 lines of code. So instead of having to do this manually every time, 2 for loops that go from 1 to 6 or from 0 to 5. And so I and j are basically these numbers. So I is this column and j is this column. And then I need to map I to the corresponding n1x or n1y and so on. So all I need to do is put this n1x, n1y in an array that I can just read from, 1, 2, 3, 4, 5, 6. So that is the assembly. Again, you can do it manually, like entry by entry, but it's 36 lines because this is a 6 by 6 matrix. Not very efficient. So I think I would rather do the this way. Okay, so for element 2, the nice thing about this is that for element 2, all I need to do is copy, paste, and I just need to change this. I just need to change the element. It will change the nodes, and once it changes the nodes, it will change the xy coordinates. It will calculate the correct B matrix. It will calculate the correct area. The stiffness is the same, so the material properties are the same. And then here is just the area times the B, which now is calculated with the correct nodal coordinates. So very easy. This is the stiffness matrix for the second element. And then for the assembly, all I need to do is the exact same thing. So I need to copy also this. Let me copy this first for the assembly. Copy that, and then copy this. There we go. So now if I do that, then now I have done also the assembly into the case. Do not run this multiple times, because every time I do this plus equal means that I keep accumulating. So this should only be run once, same as this. So yeah, only one time, otherwise it will be incorrect. Actually, let me make sure that I run the thing only once, so that otherwise it will keep on adding to the stiffness matrix. All right, so that takes care of the stiffness matrix. This is the global stiffness matrix. It's a big matrix. It should be 2 times the number of nodes times 2 times the number of nodes, so 16 times 16, because why is it 16? Was the number of nodes was Oh, this is too big, I feel. There's only 4 nodes, no? So it should be 8 by 8. So I must be doing something wrong, because it should just be 8 by 8. Sixteen by 16. Where did I? Oh, zeros. It should, but this should be. Oh, sorry. Why did I multiply here by 2? It should just be like that. Okay, so now it should be correct. Finally, let's do the force vector very quickly. For the force vector, is a constant force vector. So if you remember, I don't think I have it in these slides, but the force vector is just gonna be 0 for the x, and then the y force is minus gravity, which is 10 times the thickness times the density, which is 1. So 0.1 times 10 is 1. And then I don't have it here, but I'll do it here as well. So I just do the force vector here. So force vector is just A over 3 times bx by, bx by, bx by. So Fe1 is just the area of the element over 3 times MPRA. And again, this is just bx by. I'll just put it here. So bx is 0, by is minus 0.1. So bx by, bx by, bx by. So this is the force vector, and then for the second element, this is for the assembly. For the assembly, what does the assembly look like for the force vector? Is gonna just require one for loop. One for loop, and then because all I need to do is I still need to define the global force vector, and I plus equal Fe1I. But I'll go back here, and so the same way that I'm defining the global stiffness matrix, I'm gonna define a global force vector, which is 2 times the number of nodes. And now I assemble both the stiffness and also the force vector, and then for the second element up to here, and then let's do the force vector here. Let me just put, it's the same, so I don't really need to change anything. Yeah, so the force vector is just the same. Area of the thing that changes is maybe the area of the element. In this case, the area is also the same, but the force vector will be the same. And then for the assembly, all I need is 1 for loop instead of 2. And then I just need F and I plus equal Fe2, is that how I called it? Yes, Fe2I. And that's it. All right, so I have my global stiffness matrix, global force vector, So what is the system of equations? System of equations is going to be K, which is the global stiffness matrix, times the global D, and that one is going to equal the force vector. There's no, well, in the reactions, right? And typically also the boundary attractions, F on the boundary. But in this case, there's no F on the boundary. So if you look at this, I mean, these two nodes are the ones that could have forces, but the force is 0. So no F on the boundary. And so you can see that the first two nodes have unknown reactions. And note that it's two nodes, but the number of reactions is 4, because for node 1 there's an X and a Y, and for node 2 there's an X and a Y. So these reactions because of X and Y components. So that means that if we want to partition our system, which we can do just the same thing that I usually do. We need, so to partition the system, we need to cut matrices at 4 row and 4 column, 4th row and 4 column. Right, so if you go back to all the examples where I've done the partitioning, ME is actually going to be 4. Even though there's two nodes with essential boundary conditions, I will cut at 4. So my KE is going to be the K from 0 to NE, 0 to NE. The partitioning looks the same. KF is the matrix that goes from NE to the end. What did I just do? NE to the end, NE to the end. And KEF is the NE to the end rows, 0 to NE columns. So again, the partition is the same, but because even though I have two nodes with essential boundary conditions, each node has X and Y. So overall, there's 4 of them. And then for the F, I also need the same. So FF is just going to be F from NE to the end. And then I need the DE. DE is going to be, so this is partition K, partition F, and then essential boundary conditions. This one is a vector of zeros because the two nodes are fixed, but how many zeros? 4, 1, right? So here, note that I basically have, so X and Y components of nodes 1 and 2 fixed. And that's it. So given the partition, then the solution is going to be the MP Nash.solve of KF, and then on the right hand side it should be FF minus KF dot DE. I mean, in this case, the DE is just zeros. So this time really doesn't matter, but this is the correct formula. So that's it. So that gives us what our DF is. And there is something wrong with the, this should just be this is not correct. I think, yeah, there we go. It was solving multiple times for different values of dE. It should just be one vector, the solution. And then these are the x and the y displacements. So this is x displacement and y displacement, x displacement and y displacement of the free nodes. So these two correspond to the displacement of this one, because this is the third node, the global node. And then this last two, this minus 0.00087 and 0.00609, those two are the x and y coordinates, or x and y components of the displacement of the fourth node. And that's it. This is the, let me annotate this. Let me just print df equals u3x, u3y, u4x, u4y. There we go. And that's it. So this is the second example. I'll upload this to the elasticity folder in Brightspace, and then I'll see you on Wednesday.